Okay, welcome to another pause session. Today we are very happy to have Elisabeth Werner as our speaker, who will talk to us on random approximation of convex bodies in Hausdorff distance. Elizabeth, you take it.
Thank you, and thanks for having this opportunity to give this talk here, and in particular, thanks, of course, to Beatrice and to Katja. So as Beatrice said, I'm going to talk about random approximation of convex bodies in Hausdorff distance, and this is based on joint work with Joscha Prochnow, Carsten Schütt, and Matthias Sonnleitner. So I'm going to start with the setup and a little bit of background information. So setup is as follows. We are dealing with a convex body in RD, that is a convex compact subset of RD with non-empty interior. And we want to approximate K with a random polytope. So what do I mean by a random polytope? Well, what we'll do is we choose little endpoints, x1 up to xn. So they are IID uniformly chosen in the convex body K or on the boundary. I denote boundary like so with this partial D. So uniformly chosen in K or on the boundary of K with respect to a probability measure P. And then we'll take the convex hull of these randomly chosen points, and I'll call that Kn. So by the convex hull, I'll always denote by these square brackets. So this we call a random polytope. And also the probability measure with respect to which we choose the points, usually when the points are chosen in K, it will be the normalized Lebesgue measure, or when they are chosen on the boundary of K, it will be the normalized surface area measure of K. That's what we'll do usually. Sometimes, occasionally, I'll look at a different probability measure. Also, mostly here we'll concentrate on choosing the points on the boundary of K. Now, having this set up, we'll, of course, want to ask a natural question, which is, how good is this approximation? So what we want to do is we want to measure the error between the error, whatever we mean by this, between the convex body K and the approximating random polytope. So question, how do we measure the error? And there are various ways to do that. And one classical setup that has been used a lot is to look at the symmetric difference metric, which is nothing else but the volume of the symmetric difference. In the case when we look at such a random polytope, where we either choose, as I said, the points in the body K or on the boundary of the body K, our random polytope Kn will always be contained in the body K, and therefore the symmetric difference metric just reduces to the volume of K without the random polytope Kn. So that's one way how to measure the approximation. And the other one, which we will be mostly interested in, is to look at the Hausdorff distance. So the symmetric difference metric I denote by this delta delta. The Hausdorff distance, which we, as I said, are mostly interested in, I'll denote by this delta H. So what is the Hausdorff distance between the convex body K and the random polytope Kn? Well, it's the, so we look at, so we'll take an x in K. We look at the distance from x to the random polytope Kn, and we'll take the sup overall x in K. And then we interchange the roles of K and Kn. That gives us the second expression here, distance yk, sup overall y in Kn, and we'll take the maximum over these two expressions. Now, again, in the situation when we look at a random polytope Kn, as Kn is contained in K, the second expression actually doesn't count, and the maximum reduces to having to look only at the first expression. And of course, the biggest distance to the random polytope Kn, which sits inside K, is realized if we pick the points X on the boundary of K. So our Hausdorff distance in the case when the body is contained in K, which is the case for the random polytope, what we have to look at is the sup of sup distance xkn, where we'll take the sup over all x in the boundary of K. And here I have just written what distance K x to Kn is. It's the infimum over all y in Kn, the Euclidean norm x minus y. So that's the Hausdorff distance, respectively the symmetric difference metric. And what we are interested in are the following quantities. We are interested in the expected symmetric difference metric between K and a random polytope, respectively in the expected Hausdorff distance between K and the random polytope. So in the looking at the second expression, that's this expected distance, Hausdorff distance between K and a random polytope is nothing else but, okay, we'll take all possible choices of points x1 up to xn on the boundary of K, and look at the convex hull of these points to get the random polytope Kn, and take Hausdorff distance between K and Kn, and we average over all those possible choices of choosing points x1 up to xn in K. So it's those expressions that we want to estimate, or actually give the precise asymptotics. Now, let's look at this picture here, which shows us how these two measuring this expected symmetric difference metric, respectively the expected Hausdorff distance, how they differ. In the picture on the left, we'll see, well, it's always the same body K that we look at, and it's the same random polytope Kn that we look at. And in the picture on the left, we see that if we consider the symmetric difference metric, it's basically, we have to look everywhere on the boundary to catch where we catch our excess volume. Whereas when we look at the Hausdorff distance, it's actually only one situation which picks which is relevant for the Hausdorff distance. So this is the difference between the two setups. Of course, in both situations, as the number of chosen points goes to infinity, we get that the expected symmetric difference metric and the expected Hausdorff distance, as said, as the number of points goes to infinity, goes to 0 in both situations. And the question is, what is the speed of convergence? This is the question that we want to address. Essentially, there are two different regimes that one has to consider where the behavior is fundamentally different. One regime is the regime of smooth bodies, and the other regime is the regime of polytopes. So again, if we look at a picture, we see if we are in the smooth situation, which is the case on the left side, and we'll pick our random points on the boundary, then, well, it doesn't show so well in the upper part of the picture, but on the lower part, we see a little bit better. We'll pick up excess volume, for instance, in the symmetric difference metric everywhere. Whereas when we look at the polytope situation, it's only, well, again, choosing the points on the boundary, it's only what happens at the vertices which counts. And that has, so these two different behavior, well, which I have illustrated here basically for the symmetric difference metric, is also relevant for the Hausdorff distance. And this leads to different behavior for the two different regimes. I want to first illustrate that in the symmetric difference metric, and first look at the smooth situation. And there we have a theorem that was proved independently by Matthias Reitzner and by Carsten Schütt and myself, which says that if K satisfies mild smoothness assumptions, and I'll say in a second what the mild smoothness assumptions are, then as the number of chosen points now on the boundary of the body K, as the number of those chosen points goes to infinity, the expected symmetric difference metric of K and the random polytope, Kn, times n to the 2 over d minus 1, the limit exists and is equal to a constant CD, I have called it. This constant depends only on the dimension times the affine surface area of K to the power d plus 1 over d minus 1. So let me explain everything here. First, what do I mean by mild smoothness assumptions? They are such that we have a little r and a capital R, little r strictly bigger than 0, a capital R finite, such that whenever we take a point on the boundary X of the convex body, the ball with radius little r fits into K and touches the boundary of K at this point X. And likewise, the ball with the radius capital R touches K from the outside and contains K. Okay, so those are really mild smoothness assumptions. In other words, we'll find that the boundary of K has to be so that there exists a rolling ball from the inside, an inner rolling ball, and an outer rolling ball. So those are the smoothness assumptions. Then we'll have that the limit as the number of chosen points goes to infinity exists and is equal to this quantity here. So we'll see the dependence on the number of chosen points is n to the 2 over d minus 1. And we'll see that the dependence on the dimension d comes in with this constant cd. And I have written, it's not important, but I have written here what the constant is to show you that we know exactly what's happening in this situation. So here is the constant. It's, I believe, of the order of d. So we know exactly what it is. And also, this other quantity that comes in the affine surface area of K shows the dependence on the body, namely in form, it comes in form of the affine surface area, which is the integral over the boundary of K of the Gauss-Kronecker curvature kappa raised to the power 1 over d plus 1. And we integrate with respect to the surface area measure, which I'll denote by mu K. So this is the affine surface area. This gives us the dependence on the body. And actually, it's not surprising that this quantity comes in, because in a sense, this affine surface area, because of the Gauss-Kronecker term under the integral, kind of measures the shape of the boundary of the body. And it's natural that such a quantity should come in when one talks about approximation questions. Maybe one more word about the affine surface area. It is an affine invariant, which is of course not at all obvious if we look at this expression here. But it is an affine invariant. That's why it's called affine surface area. It's called surface area because it can be given another representation in terms of derivative of volume, and then it is reminiscent of Minkowski's definition of the usual surface area. That's why this quantity is called affine surface area. Okay, so this is nice because this result tells us exactly what we can expect with respect to random approximation of a sufficiently smooth convex body when we choose the points at random on the boundary of the body. We'll have all the dependencies of all the quantities involved. Okay. Now let's pass to the other regime in this situation of the symmetric difference metric. And the other regime is when we look at polytopes. So this is now a result by Matthias Reitzner and Carsten and myself, and it says if K is a simple polytope, so simple polytope is a polytope where at every vertex meets D facets. So for instance, the cube would be a simple polytope. Then the behavior is as follows. So the expected symmetric difference metric between K and the random polytope, where again we have chosen the points on the boundary of this simple polytope now, times n to the d over d minus 1. The limit exists and is some quantity I've called C delta of K. This is the constant that depends only on K. And we know it is strictly positive and it's finite. But with Matthias and Carsten, we haven't tried to trace the exact value of the constant going through every step of the proof. Okay. I want to compare for this result where we have chosen now points, or where we look at a result where K is also a polytope, but now we do not choose the points on the boundary of the polytope, but inside the polytope. So now we sample endpoints uniformly and IID inside K, look at the convex hull, and the random polytope that we obtain this way, I'll call Kn superscript in to indicate that it's the polytope where we have chosen the points on the inside. And then Barani and Buchta showed that the expected symmetric difference metric of K and such an inside random polytope times now n over log n to the d minus 1. The limit exists as the number of chosen points goes to infinity and is equal to the number of flags of K over d plus 1 to the d plus 1, d minus 1 factorial. And if we'll see, if we compare the two results, in particular, if we look at the dependence of the rate of convergence with respect to the number of chosen points, that is, if we compare n to the d over d minus 1 to n over log n to the d minus 1, maybe I have written it. Yeah. So I have written it here. So if we compare the rates of convergence with respect to the number of chosen points, when the points are chosen on the boundary of K, we'll get this rate n to the minus d over d minus 1. And when the points are chosen inside K, we'll get log n to the d minus 1 over n. And of course, the first quantity, the first number is much smaller than the second number, which is obvious because when we choose the points on the boundary, we already have a chance to be closer in approximation with respect to symmetric difference metric than choosing the points inside. Okay. So to resume or to make a resume, what we have in the symmetric difference metric for the points chosen on the boundary of K, comparing the smooth case and the polytope case, we see that in the smooth case, the expected symmetric difference metric between K and the random polytope behaves like n to the minus 2 over d minus 1. And in the polytope case, it behaves like n to the minus d over d minus 1. And again, we'll see that the second quantity, looking at the polytopal case, this is much smaller than the first one. Well, if d is bigger, if the dimension is bigger than 2. Okay, so that was a little bit about the symmetric difference. Yeah.
Regarding your last slide, the one just before, is there a geometric? No, the one with the conclusions. Is there for the symmetric difference? Is there a geometric interpretation of why the second number is much smaller when the dimension is large?
Yeah, I think maybe it's this picture that I showed at some point, right? If you choose the points on the boundary of the polytope, right? Only at the vertices something happens where you can, because now we choose the points on the boundary, right?
I
So
see.
you can only, pick up excess volume at a vertex, right?
And these are few compared to the rest of the boundary. I see.
Right, and whereas if you have a smooth body, you have more chance to pick up excess volume.
I see. Okay, thank you.
Make sense? Make sense?
Yeah.
Okay. So that was the setup with respect to symmetric difference metric and points chosen on the boundary of K. And now let's pass to the Hausdorff distance. So with respect to symmetric difference metric or other metrics related to intrinsic volume, there is a huge amount of literature, whereas concerning Hausdorff distance, there is not so many results. So in particular, we were not able to really find results of the form we are interested in, namely the exact asymptotic behavior of the expected Hausdorff distance of a given convex body K and a random polytope. That is results of this type here, limit n goes to infinity, an expected Hausdorff distance K, Kn is equal to some C of K. When the points are chosen on the boundary, we couldn't find such exact asymptotic behavior results. What we did find is upper bounds for convergence almost surely by Dümken and Walter. There are some results by Brunel, but also not giving the exact asymptotic behavior. However, there are some results when the points are chosen inside K, and I want to mention those now. So random points chosen inside K, and we look at the Hausdorff distance. So in dimension 2, there are results by Breker, Hsing, and Bingham for smooth. So they have results for, again, we are looking at the two regimes, smooth bodies and polygons, and Breker, Hsing, and Bingham, they have results in both situations for smooth bodies and for polygons. Namely, what do they have? Well, let me give you the setup, which I already mentioned, but I'll give more details now. So K is given. We now choose IID uniform in K, and not on the boundary of K, random points y1, y2, up to yn. We look again at the convex hull, and that gives now our random polytope Kn superscript in to denote that we are inside the body. And then the result by Breker, Hsing, and Bingham says that if K is a polygon in R2 with m vertices, then, well, they have a result about the convergence of the distribution function, but not a result that we really want, which is a result on the expected Hausdorff distance between the body and a random polytope. So what they have is this result here on the distribution function as the number of points goes to infinity, little n, then the probability that n to the 1/2 Hausdorff distance between K and this random polytope inside K is smaller or equal than X is equal to the product I goes from 1 to capital N, and then comes 1 minus pi of X. And I have not written what the function pi of X is. It's a function that depends only on the interior angle of K. And I have not written what the function pi is. They have an explicit expression of this function. I do not want to write this now because we'll get to a result of Joscha and Matthias and Carsten and me later, where a similar expression, a similar function occurs, and I'll explain then things there once we get to this point. So we do find a result in convergence of the distribution function, but what we want is a result on the convergence of the expected Hausdorff distance. In dimension bigger than 2, again, the points chosen inside the convex body, there is work in progress by Pierre Kalka and Joe Jukic, which should appear probably soon, and they have very precise results actually on the behavior also of the expected Hausdorff distance. Again, in the inside situation, that is when the random points are chosen inside the convex body K. So that was a short detour on random points chosen inside the body K and the Hausdorff distance. Let's now march to the Hausdorff distance where we choose the points on the boundary. We'll again consider 2 regimes, smooth bodies and polytopes. So let's start with the smooth bodies and the Hausdorff distance when the points are chosen on the boundary. So what's the setup? K is now really has enough smoothness, is a C3 plus convex body in RD. So C3, it is 3 times, boundary is 3 times continuously differentiable, and the little plus stands for that Kronecker curvature at every boundary point is strictly positive. And we look at a probability measure P, where we now hit the surface measure mu K with H. So H is a strictly positive density, that is C1, and it's normalized, so that's a probability measure. And with respect to this probability measure, we choose points on the boundary of K, points x1 up to xn, and look at the convex hull, and that gives us again our random polytope Kn. Then the result by Klasauer and Schneider says that the Hausdorff distance between K and this random polytope Kn times n over log n to the 2 over d minus 1, the limit as the number of chosen points goes to infinity, converges in probability to the quantity here on the right-hand side. So what's the quantity on the right-hand side? Well, it's 1/2. Then comes 1 over the BD minus 1, 2 volume. So this this quantity here is nothing else but the D minus 1 dimensional volume of the D minus 1 dimensional Euclidean ball. And then comes maximum over all points on the boundary X on the boundary of K. And it's again the Gauss-Kronecker curvature kappa x to the power 1/2 time over the function h of x that comes in, and everybody raised to the power 2 over d minus 1. So this is kind of normal, natural again, that the Gauss curvature should appear in the smooth situation if we want to see how the behavior is when we measure how good the approximation is with respect to the Hausdorff distance, because at a point where the Gauss curvature is large, we should expect that we are furthest away. We are furthest away from the random polytope. So it's natural that this kappa of x comes in, or actually the maximum over kappa of x comes in. So, but this is not exactly what we wanted, because we have here a convergence in probability, and we wanted convergence in expectation. But then it turned out, looking at dealing with the proof of the result that I'm going to mention in a moment, we saw that our result also first had some convergence in probability, and with a good tail estimate and some other ingredients, we could actually pass from convergence in probability to convergence in mean. And then we realized that we can do that also for using this result by Klasauer and Schneider. We'll get actually under the same assumptions as Klasauer and Schneider have, we'll get the convergence in mean. So we'll get same dependence on the number of chosen points, n over log n to the 2 over d minus 1. Then the expected Hausdorff distance between k and the random polytope, that's the same as in the Clauser-Schneider result above. The limit as n goes to infinity exists and is now equal to the same expression as in the Clauser-Schneider result. And actually, we not only have the expectation that is the first mean, we can show that expectation in p mean also we can show that also that this converges with the same methods basically. Okay, so this is the smooth situation, and as I said, in the Hausdorff distance, we also have to distinguish between the smooth regime and the polytope regime, and situations different in the two different regimes. And let's now pass from the smooth regime to the polytopal regime. We already realized that for polytopes, everything happens at the vertices. So if K is a polytope and we look at the Hausdorff distance between K and the random polytope Kn, we've already seen as the random polytope is contained in K, the Hausdorff distance reduces to looking at the sup over all x on the boundary of K, the distance of x to Kn. But now, this reduces further when we are in the polytopal case and we choose the points on the boundary, reduces further to just looking at the distance of Vi to Kn and the maximum thereof, where we'll take the maximum over all the vertices V1 up to Vm of K. Right? So that is probably clear. And now, what we want is what we also already always looked at so far, and what we always also already realized for the Hausdorff distance in the smooth case. We want to get exact asymptotics for the limit as the number of chosen points goes to infinity of the expected Hausdorff distance between K and the random polytope Kn, where K itself now is a polytope. To indicate a bit what we can expect and to see what we could find in the literature, I want to mention this one result that we actually could find, but that was an inside result, that is the random points were not chosen on the boundary, but inside the polytope K. So this is a result by Barani that says for n large enough, the expected Hausdorff distance between K and a random inside polytope times n to the 1 over d is bounded above by some function C2 of K and bounded below by some other function C1 of K. So they are both strictly positive and finite, but they differ, and they differ, and one doesn't know the exact behavior. Seeing this result by Barani, it was easy to show that if K is a polytope, and now we choose the points on the boundary of the polytope K and not inside, then we'll get a similar estimate, namely the expected Hausdorff distance between the polytope K and the random polytope Kn, now times n to the 1 over d minus 1, is again bounded above by some function C2 of K and below by some other function C1 of K. And of course, they are not the same C1s in the situation inside and on the boundary. We'll just call it by the same name because we don't really know what they are exactly. We know they exist. So that was not quite satisfactory, but already one thing we learned from this, namely we learned the dependence on the right dependence, at least on the number of chosen points when we choose the points on the boundary. And this dependence is n to the 1 over d minus 1. But as I said, what we really want was the exact asymptotic behavior. Before I get to that, let's now compare the two regimes when we look at the Hausdorff distance where the points are chosen on the boundary. So in the smooth case, we know the expected Hausdorff distance between the smooth convex body K and the random polytope behaves like log n over n to the 2 over d minus 1. And we know the exact asymptotics there also, as we showed in this result using the Glasauer-Schneider. And at least in the polytope case, what we know so far is the dependence on the number of chosen points. That is when K is a polytope itself, and then the random polytope in the Hausdorff distance expected difference metric is like n to the minus 1 over d minus 1. But what we want to know is what is the exact asymptotics also in the polytopal case. Okay. And that is what we could answer so far in dimension 2. So what we did with Joscha and Carsten and Matthias is that if K is a convex polygon in R2 with m bigger or equal 3 vertices, then the limit as the number of chosen points, the points that we now choose on the boundary of the polygon, goes to infinity, n times, which is the right order as we just saw, if d is equal to 2. The expected Hausdorff distance between K and the random polytope, Kn, where we choose at random the points on the boundary of the polygon, behaves like the right-hand side here. So what does the right-hand side involve? It's a bit unpleasant. First term is still nice. It's nothing else but the boundary, the volume, or the one-dimensional, the surface area of the polygon. And then it's involving one integration with respect to x, and then another inner integration with respect to variable y. And so it's a bit a complicated expression. We also see that it involves a product. J goes from 1 to n, where the number of vertices are actually m. The number of vertices is actually m, and it involves an angle alpha j, and alpha j is the interior angle at the vertex vi, or vertex vj. So you may not remember when I mentioned this result by Preker, Hsing, and Bingham. It also involved a product 1 minus pi of x, and actually, these PI's expressions that appear in their result are kind of similar to our to this expression that we'll get here. This double integration with respect to x and then integration with respect to y. Now let me explain the things that appear on the right-hand side here. So there is an integration bound Lj. So what is the integration bound Lj? Like the alpha j, this is related to the interior angle alpha j at the vertex vj. If the interior angle alpha j at the vertex vj is strictly smaller than pi over 2, the Lj is simple, it's just 1. If the interior angle alpha j is bigger or equal than pi over 2, then the Lj is 1 over sine alpha j. So that explains the bound of the integral on the right-hand side. Now, under the integral here, we'll have the exponential function e to the minus x times y plus h y alpha j. So the question, of course, is what is this function h? So let me explain that next. Here it is. it's also a bit involved, and we have again to look at cases, namely if alpha is smaller than pi over 2 and y is in the interval 1 over cosine alpha, or if alpha is bigger or equal than pi over 2 and y is bigger than 1 over sine alpha, then the hy alpha is simply well, simply or not simply y times sine alpha, y squared minus 1 root minus cos alpha over y squared sine squared alpha minus 1. And in all the other cases, hy alpha is equal to 1. Okay, that looks a bit strange. Where does it come from? Actually, it turns out that this function hy alpha is appearing quite naturally in the context of the question that we are asking. And it can be explained geometrically that this hy alpha must appear. So let me try to explain this. So what's going on? What's happening? So we are looking at our polygon K, and I only show here a part of the polygon K. Namely, we look at the vertex VI here with interior angle alpha I. Then what we want to do is we want to see how far this vertex VI is from a random polytope where we choose the points at random on the boundary that is on those edges of our polygon K. Now we know that this vertex VI is distance x away from the random polytope when the situation is like what I have drawn here. All the chosen points lie below this line here on the edges. In other words, what do? We know that we have a chance to be distance x away from the vertex with our random polytope if we draw a circle with radius x around our, with radius x centered at VI, around our vertex VI, we draw this circle with radius x. Then we look at tangent lines to these circles. Here I have drawn one, this one. Now, if we choose all points below this, all points of the approximating random polytope below this tangent line, then we know that our vertex VI is distance x away from this random polytope where we have chosen the points below that. Okay, so if we start our tangent line on one edge at distance x times y from the vertex VI, so on this edge here, we are at distance xy from the vertex VI, we draw the tangent line to the circle, then this tangent line intersects the other edge at distance x times h, exactly this function h y alpha I. So this is now the distance from the vertex VI on the other edge. So that's the geometric interpretation of this function h. So it does appear quite naturally in our context. Okay, so I have written again our result that gives us the exact asymptotics of the expected Hausdorff distance between the polygon and the random polygon. And I've tried to explain that more or less these expressions appear in a natural way in the situation that we are considering. I should also say that first we had a proof of this result that was very technical and quite elaborate and long. And then we actually, and what we actually did, we did discretization of the edges and computed exactly the probabilities. And that took lots of computations, and then at some point we realized that we can simplify things a lot by, instead of doing this discretization and computing the probabilities, we can simplify things by looking at the Poisson point process. And that way we could reduce the proof by half, and we could reduce the paper by half using Poisson point process. But nevertheless, the expressions that we have here on the right, so these integral expressions are a bit, one wonders, okay, what is actually the actual size of these expressions, or what do they mean? And to illustrate that, let's look at a special case when the alpha I are bigger or equal than pi over 2 for all I. So when that's the case, then we'll get the following corollary. So again, K is a polygon in R2 with M vertices. Now we make the special assumption in addition that the alpha i's are all bigger or equal than pi over 2. Then the n times the expected Hausdorff distance between K and Kn behaves like C of K, modulo an absolute constant. So what's the C of K? It's the quantity that I have written here. So it's again the length of the circumlength of the polygon. And then comes a summation. K goes from 1 to m minus 1 to the K plus 1. And then we'll get a sum over all possible choices, K of K tuples of interior angles alpha ij. And we'll sum these sign expressions of the interior angles. So that looks much more friendly. The expression that we have now looks much more friendly than this expression that we have up here. And we see really the influence of the interior angles, how it comes in this approximation question when we deal to have an approximation of such a polygon. So let me show you the proof of the corollary. So I have written the general theorem again, but now we are in the situation that all alpha I are bigger or equal than pi over 2. That means that, you may not remember, but we are in the situation that then all Li are equal to 1 over sine alpha I, which means that in the inner integration, which is the integration over y, we'll have that y is bigger or equal than sine alpha I. That means something for our function h y alpha I, which is under the exponential. I've written here again what the function h is, the function h y alpha I. It's this function here. Now we know that y is bigger or equal than 1 over sine alpha I, and I have written this estimate here. And then comes the rest, about which we don't really care. The only thing that we want to realize that this whole expression is bigger or equal than 0, which is the case because actually one can show that the function h y alpha I is positive if y is equal to 1 over sine alpha I, and then it is monotonely decreasing, going to 0 as y goes to infinity. Well, that it goes to 0 as y goes to infinity, we can see here easily, because notice that we have on the top, we'll basically have as y goes to infinity, the dependence is y, and we'll divide by y squared. So as y goes to infinity, it goes to 0, but it's decreasing. And it's bigger or equal than 0. So that helps us to estimate the inner integral. And I'll give only the estimate from above for the expression. The estimate from below goes similarly. So consequently, this inner integral, the y integral, this one here, we can estimate by smaller or equal than x integral from Li to infinity, e to the minus xy, because I can simply drop the function or the term that comes from the function h, because the function h is bigger or equal than 0, as we have seen here. And this now we can integrate, so we'll get e to the minus x Li, but Li is 1 over sine alpha, so we'll get e to the minus x over sine alpha I. Good. So that settles the inner integral, but we also have to take care of the rest. So the rest would then be looking at the product. I goes from 1 to m, 1 minus x times this integral dy, which is, of course, simply now putting in what we have realized on the integral, bigger or equal than product. I goes from 1 to m, 1 minus e to the minus x Li. Okay, here is our general expression again, and I have written our estimate that we have arrived at so far. That's coming exactly from the previous page. Nothing has happened. But now we'll have to, what we'll do next is we multiply out this product. So, and actually right away look at the expression 1 minus this product. So 1 minus this product is then smaller or equal than 1 minus using our estimate from above. And now we'll multiply out this product, which is not difficult. What we get is exactly this. We'll see, for instance, one sees already that the 1 disappears if we multiply out this product here. And what we'll end up is exactly that expression here. And that now, on that now, we'll have to do the integration with respect to x, but we'll see this can also be done. So doing the last step, integrating this expression here with respect to x gives us what we claimed. All right, so I'll take, I guess I should finish. I'll take one more. So that's what we get. I showed you the upper estimate. The lower estimate is a bit more technical, but can be done similarly. I want to show you one more corollary because, okay, this is now a nice expression or nicer expression that we had earlier, where we had these double integrals or these two times these integrals. And now we'll have this sum over the inner of the sine over the inner angles. And if it so happens that we have a regular polygon, and that's what the next corollary is about. So if we have a regular polygon in R2, which I'll denote like so, K regular, that is all the inner angles alpha I are the same, then this expression here involving the sum of the inner angles simplifies further, and it finally reduces to the expression here. The limit as the number of chosen points on the boundary of this regular polygon now, Hausdorff distance between the regular polygon and the random polygon behaves like that is up to absolute constant time. It behaves like the surface area or the circumsize of the regular polygon times log m over m, where m is the number of vertices or the number of inner angles. And yeah, I guess I should stop and yes, thank you.
Thank you, Elisabeth. Are there any questions or comments? I had a question about, in the prior results that you showed, I don't remember now the authors. The upcoming work by Kalka and Jukic, as said, that's for higher dimensions, right?
That is for higher dimensions,
and
yes.
Inside the approximation.
Inside is there any of these higher dimensions, yes.
Is there any hope with your methods to also get something in higher dimensions for approximation?
Of course, very natural question, right? So in the smooth case, we actually do have the higher dimension result, right? Oops. Now I can't go back, but now I can go back. I have just to look at a different. So in the smooth case, we actually do have a higher dimensional result. So it's this one, right? Which simply follows using, as I said, the Glasauer-Schneider result, and one has to use another result by Dümken and Walter, and one has to do a good tail estimate, and then interchange integration and limit with a dominated convergence theorem, and then use Glasauer and Schneider. That gives us this. Of course, for the Polytope case, now we only have this result in dimension 2. It was pretty hopeless in our original proof, where we did discretize the edges and then exactly computed the probabilities of the various events. It looked maybe possible to do it in dimension 3 with a lot of additional work. But now that we realized, we can actually use Poisson point process, we are actually hoping that this might be possible to also extend then to higher dimensions. But the thing is, if you look at the expressions that we get here on the right-hand side, they are already pretty involved in the two-dimensional case, and it's not clear. I mean, we are a bit more hopeful now with this Poisson point process realization than we were before. But as I said, looking at the expressions on the right-hand side, maybe dimension 3, and we will try.
I see. Thank you. Any more questions or comments? Okay, if not, let's thank Elisabeth again for the very nice talk.
Thanks very much, and hope to see you soon.
Yeah, of course.